Hello everyone and welcome to the third HySolChem lecture of our MOOC project. This lecture is about cation exchange membranes. My name is Stef Depuydt and I am a PhD student at the University of the KU Leuven. And if you want to know more about cation exchange membranes, you can always write me an email on this email address. So let's get started. This will be the outline of the presentation. I will discuss the different membrane types. I will go more into detail of on cation exchange membranes, and I will tell you more about the synthesis of those membranes. So, first of all, when people say a membrane, most people think immediately of those membranes, of those kind of filters that filter out components that are big and that are not able to go through the holes of the filter. And that's indeed the mechanism of how the pressure-driven membranes work. With those pressure-driven membranes, we have a pressure difference that's a driving force for the separation. What happens is shown in this scheme. So we have a pressure that's applied over the membrane. On the top, there is a higher pressure than at the bottom. So components will be pushed through the holes. And as you can see, the holes are rather small, so these red big components will not be able to permeate through the membrane, and only these smaller blue ones and these smaller orange ones will be able to permeate through. And this is a way how we separate the big components from the small components. This separation is based then on size exclusion effects and on solution diffusion. There are different types of pressure-driven membranes. We have microfiltration membranes, ultrafiltration, nanofiltration, and reverse osmosis. The difference between them is that the pore size of those membranes decrease, such that we have in each step a different type of compounds that we can reject, so a different type of separation. Of course, the smaller the pore size, the higher the pressure that is needed for the separation. Those are pressure-driven membranes. The membranes we will be focusing on in this lecture are ion exchange membranes. These ion exchange membranes, they use a potential difference as a driving force. There we have a separation that's based on a charge. There we have two types of ion exchange membranes. We have cation exchange membranes that are selective towards cations, meaning that cations are transported through the membranes and anions are rejected. And then we have anion exchange membranes. Those are membranes that are selective towards anions. As we look at the scheme, at the left side here, we have cation exchange membranes. So we have an anode, we have a cathode. Cations have the tendency to go from anode to cathode, and they are able to do so because this membrane contains fixed negative charge regions that are present in the membranes. So these sodium ions will hop from the one negative region to the other one, and that way they will be able to transport through the membranes. While here we have an anion. Anions have a tendency to go from cathode to anode. These will not be able to move through the membrane because these fixed negative regions are repelling the anions. So they will just be repelled, and we have only cations that can go through. For an anion exchange membrane, the opposite is true. There we have anions that now are able to move from cathode to anode because now the membrane has fixed positively charged regions, and the cations are blocked and they will not be able to go to the cathode side. Although I said at the start of this presentation that the first thing we think about when we say membranes, that those are the pressure-driven membranes, there is a whole wide range of applications for which we can use ion exchange membranes. For example, a hydrogen fuel cell that can be used in cars that drive with hydrogen gas. What happens here is we have hydrogen gas that enters the compartment. This hydrogen gas reacts with the anodes that will take the electrons from the hydrogen gas and transport it via an external circuit to the cathode side. So there are electrons going from left to right. So to close to close the balance, the electro balance, we need also a transport of cations going from left to right. And those cations are these hydrogen ions, these protons, and these will be able to go through a proton exchange membrane that's in the middle. A proton exchange membrane is just the same as a cation exchange membrane, but specifically for protons. So we have here also a cation exchange membrane, a proton exchange membrane that is used in this application. There are a lot of ion exchange membranes that are used in electrodialysis. Electrodialysis can be used, for example, to desalinate brackish water or to remove heavy metal ions from wastewater. How it works is we have a stack of ion exchange membranes where cation exchange membranes are alternated with anion exchange membranes. And we apply again a potential difference. What happens is we have a feed coming in here. Here we have, for example, sodium chloride. So we are now desalinating brackish water. We have here a compartment with a cation exchange membrane on the right and a anion exchange membrane on the left. The sodium will be able to permeate through towards the cathode, and the anion will be able to permeate through towards the anode. So this way we are creating here a diluted compartment, while on the other side here, this is the ion receiving end. There sodium will arrive and chlorine will arrive, and these sodium and chloride are now stuck here because the sodium cannot transport further because suddenly there is an anion exchange membrane. This way, with electrodialysis, it is possible to create concentrated compartments with ions and diluted compartments with ions. So this way we can desalinate brackish water. The most interesting application for our ion exchange membranes is for sure the HySolChem process, the HySolChem project. If we look again to how this process works, we have an anode here. This anode will degrade organic pollutants and microplastics and will set protons free. We have an electron current from anode to cathode via an external circuit. So electrons go here. So now we need to close this charge balance of this process. And that is, we can do that in two ways. Either we transport cations from left to the right, or we transport anions from the right to the left. Now, in our HySolChem process, we collect at the cathode side, we collect negatively charged products. Think about formic acid, acetic acid, that is all produced at this photocathode. So we don't want anions to transport from the right to the left side, because that way we will lose those products. What we want is only a transport from cations, from protons, from the left to the right then. So we are in need of a proton exchange membrane or of a cation exchange membrane in between. So that's why it's important for our project to synthesize a good working proton exchange membrane. Now, I told you before that such a cation exchange membrane has fixed negatively charged regions. These regions are very often sulfonic acid groups in a polymer, because most membranes are made out of polymer. What happens? We have here, for example, a polyether-ether keton polymer that's sulfonated with such a sulfonic acid. When this polymer is in water, this polymer behaves as a strong acid, so it will deprotonate, so the proton will go free. So we have a mobile cation that can move around in the solution, that can move around over the membrane, and we have here a fixed negatively charged group that stays behind. And it's this sulfonic acid anion that is this fixed negatively charged regions in our cation exchange membrane, and this will be the reason why we can transport cations and why we are repelling anions. Now, of course, there already exists cation exchange membranes. The most used cation exchange membrane nowadays is a Nafion. We see here the polymeric structure of Nafion. Nafion consists of a hydrophobic backbone and a hydrophilic side chain. Why is the side chain hydrophilic? That's because here in the end we have again our sulfonic acid anion. The presence of this hydrophobic backbone and hydrophilic side chain can create nanophase separation. So our side chains will be attracted to each other and will form regions where all side chains go together, and the same for the backbones. This way we have a hydrophilic region all through the membrane. All these side chains, of all these side chains, and this will create very efficient conducting channels for our cations to move through, because now all our sulfonic acid groups are located together. Why is Nafion also a very good membrane? We have a lot of fluorine groups on this membrane, and this increases the acidity. That will make sure that our sulfonic acid group will deprotonate even easier, and it increases the thermal and chemical resistance of our membrane. Now, besides this very good performance characteristics of the membrane, there are also big disadvantages of this membrane. The first disadvantage is lies within the fact that fluorine is used for a membrane, because this results in PFAS pollution. PFAS pollution is a very hot topic today. The PFAS stands for the fact that we have fluorine artificial synthesized polymers that get into the environment, and because they are so resistant, they stay in the environment and have all the health and environmental issues as a consequence. The other very big disadvantage is that the membrane has an expensive and non-sustainable production process. So this brings us to the goal of HySolChem with respect to the membrane, which is mainly making an alternative cation exchange membrane that is more low cost, that has a more sustainable production process, and for sure where we don't have this PFAS pollution. There are different options how we can manufacture that membrane, and we will go for the concept of using a sulfonated polymer backbone. So we have here a backbone indicated in black with the sulfonic acid groups in yellow, and we will cross-link this backbone using a cross-linker. This way we have the sulfonic acid groups that gives the functionality. We have the sulfonic acid groups that will that will give the membrane conductivity of cations, and we cross-link it such that the membrane is very dense, so that all the products we generate at the cathode side are not able to permeate through the membrane to the anode side. So we cross-link it. We want a dense structure so that we can retain all the products that we form. And now we will do some organic chemistry. First of all, how do we make such a polymer? In the HySolChem project, we chose to use polyether-ether keton as the polymer backbone because it is low cost and we can easily sulfonate it. The sulfonation follows the reaction mechanism of electrophilic substitution. How does it work? We use sulfuric acid to sulfonate. And actually what happens is this sulfuric acid will, at some temperature, go into a form of SO3H+. Now, this sulfur is quite positively charged because the group is positively charged, and it will be attracted to a benzene ring. It will be attracted to an electron-rich region. So in a benzene ring, which is present with polyether-ether keton, then this can go to the sulfur, and we can this way form a sulfonated monomer, like we see here in this example, benzene sulfonic acids. For our polyether-ether keton, for our peak, we will see then that we have here a sulfonic acid group on the benzene ring that's the most electron-rich. So if you know a bit about organic chemistry, then you know that ether groups in a polymer are electron donating, so they will donate electrons to the benzene ring. A keton group is electron taking. They suck electrons from the environment, which makes this benzene ring much more electron dense than the other benzene rings. So we will have the sulfonic acid group on this ring. So this is how we make the sulfonated backbone. Now we need to cross-link this backbone. We chose to do the cross-linking via the Friedel-Crafts reaction because we chose this cross-linker, alpha-alpha dichloropyxylane. We use this one as cross-linker because it's relatively low cost and it is relatively non-hazardous. How does Friedel-Crafts work? Therefore, we need a catalyst. We chose the catalyst aluminium chloride. Aluminium chloride is able to take a chlorine ion of the cross-linker. Now, in this example, we have a different cross-linker just to show you how it works. So the aluminium chloride temporarily takes a chlorine from our cross-linker, which makes a cross-linker positively charged. So again, this positively charged group will be attracted to the electron dense ring of, for example, to the electron dense spot of, for example, a benzene ring, and will bind to with it. Then hydrogen will get off, will bind with the chlorine that was temporarily borrowed by the catalyst, which gives this byproduct. But then we have here our crosslinker attached to the benzene ring. For our sulfonated polar ether-ether keton, then we will have this reaction at an elevated temperature that you see the chlorine of the crosslinker will be removed from the crosslinker, and it will attach to the benzene ring of the SPEAK, of the sulfonated polar ether-ether keton. Again, you see here, this will crosslink on the same ring where we also have the sulfonic acid groups, because this ring is the most electron dense. This is also to take into account for our specific case of our HySolChem membrane, let's say, is that the sulfonation reaction and the cross-linking reaction are actually competing with each other. So that's something to take into account. Then there is the last choice you need to make when you synthesize a membrane, and that's the choice of a solvent. This solvent needs to dissolve polymer, cross-linker, and catalysts. You can use the Hansen solubility parameters to determine if a component will be able to dissolve in a solvent. There are 3 Hansen solubility parameters for every compound, for every polymer, and for every solvent. We have delta H that is related to the energy of the hydrogen bonds of our compounds. Delta P is related to the energy dipolar intermolecular forces, and then we have delta D, which is related to the energy dispersion forces. We can use these 3 parameters as coordinates to put the compound in a Hansen space, like here. We have, for example, the membrane polymer here with a certain delta D, delta H, and delta P. And then we also put our solvents there with the coordinates. And then we can see that solvent, in this case, it's solvent 1 and solvent 2 is much more close to the membrane polymer. So solvent 1 and solvent 2 will be the better option to dissolve our membrane polymer. We have traditional organic solvents like DMAC, NMP, and DMF that are used a lot, but they have the very big disadvantage that they are carcinogenic, so they are very toxic. That's why it's also what we try to do is to use green organic solvent as an alternative, and there we are quite pioneers in it because the use of those green organic solvents is very rare so far for cation exchange membranes. I list here Tamisolv and DMSO that are potential candidates for us to make our membrane. Now here you see the steps actually then how you make the membrane. We use peak pellets. So we put the peak pellets in concentrated sulfuric acids. These peak pellets, they dissolve in the sulfuric acids, and at an elevated temperature, then we will have here the sulfonation. Afterwards, we have our speak, and then we will wash the speak in water, we dry it, and then we have our speak. This speak we will put then, we do it in a flask. You can do it wherever you want, but you need to make sure that you make the atmosphere inert with nitrogen gas, and then we add our catalysts, our speak, and we add our crosslinker, and we mix it until a viscous casting solution. This casting solution you can pour into a casting knife that you then move over a glass plate. So you spread the casting solution over the plate. Then here we have a liquid layer containing the solvents, the speak, the catalyst, and the crosslinker. We will evaporate the solvent that is gone. Now we have only a solid layer left with the right thickness and all the ingredients. This one we will heat up. The chemical reaction happens, the cross-linking happens, and that gives us a firm membrane, thin membrane sheet, as you can see here in the pictures. So this is everything we wanted to tell you about cation exchange membranes. You can also find our project on the Facebook page and on the LinkedIn page. And again, if you have questions, you can always contact us.